Welcome to this explainer. Today, we are going to demystify a process that honestly sounds a bit like science fiction, but it's happening every single day. We're talking about how we translate raw, unfiltered satellite data into clear, usable maps that actually tell the story of our changing planet. It is a fascinating journey from raw pixels to real meaning, so let's get right into it.
Okay, let's dive into this with a massive question. How does a computer actually know what a forest looks like from space? Every single day, this huge fleet of satellites is beaming back endless terabytes of imagery to Earth. But without a way to automatically interpret all that data, well, it's just a giant digital mountain of colored squares. Figuring out a way to automatically sort a dense forest from, say, a concrete parking lot is literally one of the most critical challenges in remote sensing. And the solution to that challenge is brilliantly illustrated right here. Take a look at this classified map of Hays City. Researchers didn't just sit down and color in those green areas by hand. No way. Instead, machine learning algorithms turned millions of raw pixels into a fully categorized landscape, achieving an impressive accuracy of over 82%. This right here is the absolute magic of remote sensing classification at work.
Here is a quick look at our agenda for today's explainer. 1. Mapping Earth from space. 2. What is supervised classification? 3. Algorithms and training data. 4. Advantages and limitations. And finally, 5. Real-world applications.
Moving to Section 1, Mapping Earth from Space. To really wrap our heads around how this works, we first need to appreciate the sheer scale of data captured by modern satellites. You see, when a satellite takes a picture, it doesn't send down a neat little label that says, "Hey, this is water," or "I'm a skyscraper." It just captures raw reflectance values. It's essentially just measuring how light bounces off the Earth's surface. So we absolutely need human expertise to translate those ambiguous pixels into something that actually means something to us. Which brings us to Section 2. What is supervised classification? Supervised classification is an image classification approach where an algorithm is actively guided by an analyst's prior knowledge of the study area. Think of it like a teacher and a student. The human analyst is the teacher. They know the landscape, so they identify and create training datasets that represent known land covers. The computer algorithm is the student. It learns the statistical relationships from those samples and then establishes discriminant rules to assign every single remaining pixel in the image to the category it matches best. To put that into perspective, you can contrast this with unsupervised classification. That's where an algorithm just blindly groups similar pixels into clusters without any prior human knowledge or guidance at all. While that unsupervised approach is pretty cool for exploring the unknown, supervised learning is what allows for highly targeted, specific mapping because our human knowledge is actively guiding the exact features we want to track.
Now, what's really interesting about this slide is seeing that whole process laid out. You can see the distinct progression, starting with a raw image, moving right into that supervised training phase, where the human provides the study guide, then the pixel labeling, where the machine does the heavy lifting, and finally an accuracy assessment at the end, to see how well our digital student actually scored on the test.
Breaking those steps down a bit more. Step 1 is gathering the training data to create that perfect study guide. Step 2 is training the classifier. Step 3 is letting the algorithm loose to classify those millions of remaining pixels. And Step 4 is assessing accuracy using independent ground truth data. Because, let's be honest, if our initial study guide was flawed, the final test scores are going to be pretty embarrassing. Let's move on to Section 3, Algorithms and Training Data.
Okay, so there isn't just one single type of digital student out there. Analysts actually choose from several common machine learning algorithms. You've got maximum likelihood classification, which relies heavily on probability to categorize a pixel. Then you have modern powerhouses like support vector machines that draw optimal boundaries between classes, and random forest, which builds hundreds of distinct decision trees to basically vote on what a pixel should be. There's also artificial neural networks and minimum distance methods, giving analysts a ton of specialized options depending on the job.
So, the crucial point here is that no matter how incredibly advanced the algorithm is, it relies entirely on the training dataset. These datasets act as spectral signatures, teaching the algorithm the very specific statistical relationship of, say, how a pine tree reflects light compared to an oak tree. If that initial signature is wrong, your entire map is going to be wrong. It's that simple.
That brings us to Section 4, Advantages and Limitations. The advantages of this approach are absolutely massive.
Because supervised classification leverages expert human knowledge and reliable ground truth data, it typically yields significantly higher accuracy than blind clustering. It's also perfect for targeted mapping when you need to match specific predefined categories. But we have to talk about the limitations. It is heavily dependent on that training data, which makes it totally vulnerable to human error.
Let's unpack those pitfalls because it's the classic garbage in, garbage out scenario. If your training samples lack variability, like say you only sample forests on completely flat ground, the algorithm is going to be totally confused when it sees a forest on a steep mountain. Or what if you have mixed pixels? Imagine accidentally circling a green park and a dark shadow together and calling the whole thing urban. The algorithm learns a confused, messy signature. And if you provide unbalanced sample sizes, the classifier might just ignore your smaller minority classes entirely.
Finally, Section 5, Real-World Applications. Let's move to the real world and see how this actually builds a better understanding of our planet. Why does this invisible digital process matter? Well, fundamentally, it's used for land use and land cover mapping. Being able to accurately separate and categorize physical patterns like water bodies, forests, bare soil, and urban built-up areas is the absolute foundation for almost all the geographic and climate science being done today.
Just imagine trying to map a rapidly growing, incredibly dense city by literally walking the streets on foot. It would be impossible, right? Supervised classifiers allow us to navigate the complexities of densely urbanized landscapes straight from space. This means we can model urban expansion over time, monitor exactly where new infrastructure is being built, and provide essential, life-saving maps for disaster management.
The value this holds for global food security is also huge. Agricultural planners rely on these supervised maps to monitor massive expanses of croplands. By identifying specific crop types and tracking their spectral signatures over an entire season, they can predict biomass, forecast crop yields, and even monitor specific forest canopy conditions to spot things like illegal logging.
And of course, it's a game changer for environmental management. By tracking spatial and temporal changes in vegetation and water bodies over decades, scientists can definitively prove where an ecosystem is thriving and where it's struggling. This provides the hard, mathematical data needed to inform ecosystem services assessments and drive global conservation policies.
The analyst provides the ultimate study guide, and the machine learning algorithm does the heavy lifting. But here is something to think about. As our planet rapidly changes, and as both satellite resolution and artificial intelligence become exponentially more advanced, how will human expertise and AI evolve together to map our future? That partnership is really just getting started. Thank you so much for joining me for this explainer. Keep asking questions, and I will see you next time.